So thank you very much for coming, having us here. I also see many girls in the audience. And last year was not so many girls, so keep it up. I'm so glad not to be the only one with a crazy laptop. And so today, we're going to do something which is in between a talk and a hands-on lab. So I'm going to start with a general talk about where we are, what we do for deep learning. For those of you that are not as familiar with NVIDIA, I'm going to mention the libraries and the platform. And I'm going to also show you the new products. But I'm going to try to make that part short, because some of you have very good access to that information. And the idea is to move to a second session where we're going to go and do an introduction to CUDA for GPU programming. So in the last days, you've seen Torch, you've seen piano, you've seen a lot of things. So I'm pretty sure a lot of you have seen GPU usage. And what I'm trying to show you here is what happens underneath the scenes and why those frameworks interact like that with the GPU, what we're trying to do to make it easier for you guys to interact with the GPU at any level, right? And then in the second part, we're going to do hands-on lab on Amazon. So most of you have a laptop. We'll give you a credential, and we'll give you a chance to try 3 different labs. So voluntarily, I opened 3 labs. I'll be mostly answering questions with Ryan on the first one, which is an introduction to GPU programming. But if you are more familiar with GPU programming, you might want to try more advanced labs. So I opened 2 more advanced labs. We will, however, focus on the questions for the first lab. OK for everybody? OK, so GPU computing. I usually start with that slide, and I like it very much. It resonated yesterday very much when Jeff Dean presented what they were doing. GPU computing is heterogeneous computing. The GPU has to be attached to something. And that something can be very different thing. It can be a power CPU. It can be an ARM CPU. It can be an x86 CPU. And that means in terms of programming, we're going to have to take care of it. We're going to have to be aware of what is underneath the scene, right? So I'm going to try to show that later. So power is mostly servers right now. ARM, it's mostly embedded right now. And x86 is what we usually got in our laptops and servers. But we're going to see later how that changes what we do. In terms of software, we're trying to be generic, so we're trying to have everything work smoothly everywhere. But there are some considerations we can't really escape. CUDA. So it's called GPU programming, and there are several ways to program a GPU. At NVIDIA, we developed CUDA some time ago. And the idea was to have a framework to program NVIDIA GPUs that makes it simple for everybody. And here, the purpose is just to show that the syntax is very close to the C syntax. OK, so that's what we're going to do later. So I'm not going to spend a lot of time on this here. But the idea is just to be able to program the GPU and to do parallel programming without having to explicitly write the loops and everything. OK, so that's an example of a sum of 2 vectors arrays in C and the GPU-friendly version in CUDA. And for most of you, it should be natural. OK? So you can interact with the GPU in CUDA or any direct GPU programming language. But you might not want to go so low level. So you might want to use a library instead. And so there are several drop-in acceleration libraries for application that we're going to see, that we see for GPUs. So here, I've made like a panorama of what we can do. So some of you might know Stress for sorting or this kind of operation. I'm going to present CUDNN and mention today cuBLAST and cuSparse very quickly. But the idea is, again, you have the GPU. You can interact directly with the GPU. You can program the GPU. Or you can decide not to be fully aware of the GPU and interact with the GPU through libraries. So deep neural net and GPUs. Why are GPUs so good at deep learning? Why are we here? And why do you care? So the reason why most of people care is what was very well actually tackled yesterday afternoon. I'm very thankful to Jeff Dean because he made my job much easier. Working on the GPU makes everything so much faster that it allows better research development by allowing quicker prototyping. And this is the very famous example of the Google data center 3 years ago, where for the first experiment, they needed 1,000 CPU servers. They needed 16,000 cores, and that was 2,000 CPUs. So most of us, we cannot handle that in our small university data center or in our local resource. And 1 year afterwards, the same people at Stanford, so people at Stanford did exactly the same experiment with just 3 servers. So that's the kind of speed up we're talking about. And that makes all the prototyping that was not feasible before feasible that way. Interestingly also, people usually say, oh yeah, but GPU consume a lot of power. I don't have that kind of power. If you look at the ratio here for the same type of computation, we like better to look at the instruction per watt, or like put that power conversation relatively to what you can achieve with it. If you have any question at any time, feel free to, raise your hand. So very quickly, recent improvements. Imagenet, most of you are aware about. The pedestrian detection, I mean, you might have heard that NVIDIA is very well versed in automotive right now too, like several companies around. So that's an example of pedestrian detection. So in black, it's regular traditional techniques. And in red, you have all the techniques that are DNN-based and that are using a GPUs. And especially for everything which is automotive related or pedestrian detection, right now we only see GPU-based workloads. And all this, like for the last part, all this was in less than a year of a time frame, right? So that was very, very quick. And that quick prototyping scheme we were talking about, that was achievable with this. cuDNN. So especially for deep learning, at NVIDIA, we developed that library that is called cuDNN. The purpose is to give building blocks to accelerate most of the deep learning neural network instructions. And it started with convolutions. It started in 2014 with the first version of cuDNN. I heard this morning something like, yeah, it depends on which cuDNN version you have. So your speed's going to depend on where you are. So I'm glad because that is what that slide is trying to show too. So right now, 2 years afterward, we're cuDNN version 5. And combining software and hardware, we managed to be 5 times faster than we were 2 years ago. So again, what was possible 2 years ago can be made twice faster. So it allows for better prototyping, but also production. Other libraries that can be used in machine learning, because usually, we see people, not everybody's doing LSTM, not everybody's doing convolution only. And sometimes people might be interested by different type of linear algebra operations. So I'm mentioning 2 other libraries. This one is called cuBLAS. It's a drop-in for the linear algebra BLAS library. So for those of you that are interested, it's the subject of the optional hands-on lab number 1. I'm not going to give more detail here. It's just GPUs are very good at linear algebra operation, and we provide different way of doing that. Same thing for the second library. It's accelerating sparse operation. It's called cuSparse. Same thing, provides a lot of matrix operation for sparse matrices that are GPU accelerated. Again, it's drop-in. You need to do that operation. You call that function. You get a result. So it's not you to take care of what the GPU is going to do. Yesterday also was mentioned something very, very interesting. We see more and more on multi-GPU workload. And we're going to see in the next session that we see also more and more of multi-GPU hardware. And it's difficult. Programming multiple GPUs and having efficient scaling is very, very difficult. But if one manages to do that, then it makes everything faster. You can work either on more data at the same time, if you do data parallelism, but you can also work on bigger models if you want to do model parallelism. So to try to make that easier for everybody, we developed that library called NCCL, NCCL. And it's a collective library. So what this means is it's a research library of accelerated routine to provide the classical operation people use when doing parallel computing, like scatter, gather, reduce. The pattern is developed after the MPI collective. So somebody mentioned MPI yesterday. We're using that kind of scheme to make sure people know the operation or find the operation they expect. And it handles every intra-node communication in an optimal way. So you don't have to worry about how imagine you have a box with 8 GPUs. And you could put 4 GPU on one CPU, 8 GPU on the same CPU, and so on and so forth. And it ends up being a nightmare of having to figure out where your data pattern is and where your communication pattern is. The purpose of this is just to make it easier for everybody, and actually not having to worry of where your GPUs are. So when you're using that library, having 8 GPUs or 4 GPUs on a single CPU is not going to change anything. Or at least it's going to be minimal for most of the cases. Again, the purpose is to make it easy for everybody. So it looks very much like the classical C approach. So this is just a small example of a single-threaded or reduce operation here. And that's how you call that library. You include that library, and you just call the null reduce, and you get the data from all the GPUs you had. And we make sure that operation is tuned for a multi-GPU platform. Question? OK, I'm moving on. I'm moving on fast, quickly on purpose, so that we can get to the hands-on. But please don't be disturbed by that, and feel free to stop me. Platform. So you might have heard that last week, if I remember correctly, we launched a new product, which is the Titanic Pascale. So you should have received an email for a raffle. The Titanic Pascale doesn't fit in my purse. So the raffle is such that we gather the email information, and we're going to send the Titanic Pascale to the winner. So yeah, I don't have the classical Titanic Pascale here today. As I said, it doesn't fit in my bag. So please don't forget to register for the raffle. Some of you did. So as you might have seen, it's very interesting because on the NVIDIA blog, you can see the detail of that card. And the first thing we say, it's 11 teraflops FP32. OK, but the second thing we say is that card can do int 8. And if you remember the talks from yesterday, it shows that that card somehow is made for deep learning development, right? We're now looking at different GPUs having different set of instructions that can do different type of deep learning operations. And so that's a card that people can use for developing int 8 deep learning workloads. So it has 3,504 CUDA cores. I'm sorry, I missed a word. And 12 gig of GDDR5X RAM. So that's the brand new product. Don't forget to enter the raffle. And yes, it doesn't fit in your bag. This one is even bigger. It doesn't fit in your bag either. It might not even fit in your car. But we hope it's going to fit in your data center. This is the DGX1. So it was mentioned yesterday that not only multi-GPU workloads were becoming more important, but also the communications between the GPUs were becoming more important. And this one is very important for us because that's the first product for which we do the full server that is dedicated to deep learning. And it uses a new type of interconnect between the GPUs, which has like a higher bandwidth than the PCIe bus that people were using before. But not only have we done that, we also make sure we took care about the I/O. In deep learning, people don't only care about compute. They only care about pushing the data to the GPU. And sometimes it can be a bottleneck. Some benchmarks are done like only on synthetic data, but in daily life, we're very conscious that if you work on images, you need to bring those images to the GPU. And this can be a bottleneck. So we made sure that this box can handle it in the best way possible. So it uses a Tesla P100 hybrid cum mesh. So that's the way the GPUs are organized. We can discuss that a bit more. And so thanks to Ryan, we brought a P100. So Ryan, do you mind come and do the presentation? And we'll have the P100 so that you can look and touch it. Don't put it in your backpack. It's not functional. And on top of it, it's like you might not have the baseball to put it on. So Ryan?
OK, so the P100, this is actually a really exciting new GPU that we've announced. And I'm going to pass it around the room so you can all get your hands on it. I think we have the next slide. That is P100. There we go. And so the first thing you're going to notice is the weight. So not only is there some super interesting hardware design going on this chip, but there's also some really interesting mechanical engineering. We can talk about that after, but there's some really cool stuff that's just going on the baseboard. The three things I'm going to talk about, just to point out from an architectural point of view, is the chip, the new GPU and the new architecture, the memory, which is completely new, and the NVLink, which is, I would say, probably the biggest and most exciting change of this whole design. So with Pascal, this is a completely new architecture. You're not going to be surprised as I'm going to tell you it's faster. It's kind of a no-brainer. But under the covers, the SM design and the microarchitecture is also completely new, or not completely new, but newer in the sense that we have a lot more SMs. Each SM is maybe a little less powerful, but we keep all the same register and shared memory units per SM. So now you have less cores per SM with the same amount of registers and shared memory, which makes actually programming for those SMs a little bit easier. Moving on to the high bandwidth memory. So most people, as you pass this around, you're going to notice the units going around the outside. And most people will say, I bet that's the memory. And you'd be wrong. So on most GPUs, the memory is outside the die. But with high bandwidth, or HBM2, we've moved the memory onto the chip. So this is a technology that we introduced called a chip on wafer on substrate. So the GPU, I'll just hold on to that. Yeah. So the GPU is a chip that sits on a piece of silicon with an interposer, and we've stacked the memory right on the die. So the benefits from that is a vast reduction in the amount of energy per memory operation. So not only can we run, we greatly increase the memory bandwidth up to 720 gigabytes a second, but we've also greatly reduced the power per memory op. And so that's a huge increase over, I think we had like 230, 280 on the previous Maxwell generation, so it's a huge step up. And finally, NVLink. So on the back, there's two plastic pins in there that you can pop off, and you can look at the actual pins. One of those connectors is for the NVLink, and the other is for the PCIe and for the power. And this is attached directly onto the baseboard, and NVLink is are traced onto the baseboard. And really, this is kind of the most unique architectural change that we've enabled with the P100, because it basically is the multi-core SMP for GPUs now. You can directly address memory for directly attached GPUs, and then you can take advantage of nickel for the communication between. So if your algorithms can make use of aggregate distributed memory, you now have 16, because we have 16 gigs of HBM2 times 8 in the DGX1. So you have 128 gigabytes of directly accessible memory. So that can greatly increase the models that you can put in there, and you have very fast access to it. And with that, I think I'll turn it back to Julie.
So what you can see, it's brand new and it's getting us very excited. We just hope it's going to get you as excited as we are. So this is for us, this is a great new, hardware improvement. But we need to be able to program that hardware, and we want everybody to be able to program that hardware. So nickel was taking care of the multi-GPU communication. Now we see a lot of people are looking at inference, right? And this is the whole scheme on how we see the world in production, where in an image, let's imagine an image workload, people would take the image, put them in a repository, augment, maybe work on those images, and work with, Caffe, Torch, Ciano. So right now in Digits, we have Caffe and Torch, where we provide a web UI to help people develop their own deep learning workload without knowing anything about frameworks. And then we train, we test, we set up a model, and we want to do inference. And when you want to do inference, you can be interested in doing inference for very different applications. OK, so this is the focus we have on inference. OK, so you have a drone, you want your drone to capture where the cars are, or you have your car, you want your car to be able to see pedestrians. And what we think is good is to develop something which is dedicated to inference, because the workload is kind of different. We see a lot of people during inference that are interested in using tricks, such as fusion. So my slides are not in the right order, but that's what it is. So I'm just going to go back there. So this is an example of an NVIDIA platform for embedded. So this is the TX1. It's a small board that people use in drone, for example. And it used to be that we had the same software stack. So this is to come back when I said the GPU has to be attached to something. I cannot comment on that right now. Each time, so what I can say is each time we have a new architecture, usually we bring that new architecture to server, workstation, and embedded. I cannot comment on the timeline. Okay? So he's right. So what he wanted to point out also is this is the previous Maxwell architecture. And what we did at the time is people would train a model, and we have the same software stack everywhere. So the fact that it's not the same CPU is transparent to the user, right? So this is an example with Caffe, where you just take your Caffe model file, and we have example on the web, and you push your Caffe model files on your TX1, and you can run inference without any modification in the code. And so we figured we wanted to do more about that, and we wanted to make that inference even more efficient. So that's also why we developed GIE. So the idea is when we do inference and we do that forward pass, we can use a lot of tricks to be faster. We can fuse the layer, we can eliminate some layer, we can specialize some kernels. We can do a lot of auto-tuning for the target platform, and we can make sure that wherever that model is pushed is going to be tuned to work better. That's what GIE is about. And so I invite you to have a look at the website. This is an example of performance numbers. So on the right, you have the classical Caffe plus GPU workload. And on the left, you have GIE plus GPU workloads. And so Ryan actually made that graph, so you can talk to him at the end. What's very interesting is sometimes you see big improvements in performance. And it's actually when we're fusing layers both horizontally and vertically, right? And having horizontal fusing brings a lot of performance impact. Yeah?
What's the y-axis here?
The y-axis is the performance, is the time for each layer. Sorry.
Yeah,
I was right?
no, it just cut off.
Yeah, I'm sorry. It's a layer time. OK, so that's for inference. I mentioned some people don't want to see the GPU at the coding level. They don't want to see the library level. They don't even want to know what a framework is. I guess that's not so many people in that audience, so I'm going to be fast. We also have a web UI called Digits that is available in the labs that you can look into if you wish. CUDA. So I'm done with the global presentation. So do you have any questions before I get into the introduction to programming and hands-on? Yes?
So when are we going to see floating point 16 on other chips?
So very good question. The question is, when do we see FP16 anywhere? On Titanic, there is no FP16. There is FP16 on the GP100. I mean, there is very slow FP16, not so many FP16 units. So on GP100, there is FP16 operations. So in the DGX1, you have FP16. We announced last month P100E, which is the PCIe pendant of the GP100 NVLink that has FP16. So it's the same chip that goes on the PCIe bus. And as of today, that's the only product we announced publicly. So right now, if you have a server that takes a regular card on PCIe, the solution for you is P100E that we announced last month, end of June, and that should be available in the fall.
So how much does it cost approximately?
I have no clue about pricing, but we can follow up that request. I don't know at all. I'm sorry.
Is there a reason why a GPU has relatively limited memory?
There's a hardware reason. Like the process, you might have heard about like 1614, the FinFET mechanism. There's only so much memory you can put on the die. And right now, when you say so few, we would say that's a lot already. You can get up to 24 gigs regular GDDR memory. That's what we've shown before. For HBM2, it's only 16 gigs right now. It's mostly because of the hardware process.
It's not the die size.
It's not the die size. It's the fact it's how much memory you can put on the die and actually the yielding of getting those die built.
The only other point I would make there is that when you're programming for a GPU, you're taking advantage of the ability to you're just taking advantage of the ability to overlap memory operations with computers. And so you don't need a lot of storage. You have registers that you context switch in and out of. and then you're using the GPU memory bandwidth as a kind of a buffer there. And so it's the ability to contact swap between different stages of your compute. As you lock on I/O coming in, you should be computing somewhere else. That's how we take advantage. And we've improved that with P100 because now you have more registers and more shared memory per SM than you did in the past architectures.
And I think the answer we made to that question is also very interesting to me because it's always a balance between the hardware and the software. So GPUs are generic programming units, right? They're not dedicated to a specific task. There are some tasks that they do well. And all those answers are going to be a combination on how you program and how the hardware is set up. So while we try to abstract as much as we can of the hardware, having an idea of how it is underneath helps. So for the CUDA part, we're going to see a lot of the register and memory. So if some of you don't know what an SM is yet, don't worry, we'll see that. It's okay. It's just, you have to have an idea of what's underneath. And but you don't have to know how to program individually. Just having an idea of the sizing underneath is sufficient, usually. Yes?
For those of us that are new to GPUs, I might be the only one, but could you tell us a bit more about the floating point accuracy and whether that or how that affects the types of models you can?
So the question is, for those of us that are new to GPUs, can you tell me the influence of the floating point accuracy on what we do, training, basically? So for FP16 and Int8, I leave the experts to reply to you. It's always, the easy answer is it's always a trade-off between accuracy and training speed, right? If you train with a lower precision, if you want to keep your accuracy, sometimes you have to be careful, especially when you want to do training. What happens in the gradient, you want to be very careful at. So there are some operations that are very easy and that have absolutely no impact in FP16. And there are some operations that are much more tricky when you're training, depending on what type of network you're training. For inference, I would say that the community now agrees that you can infer in FP16, sometime in Int8, having a drop in accuracy of less than like 5% for any kind of like AlSNet, GoogleNet, common, network type. For training, the community still, maybe you can comment on that, because I feel it's a vexed question, right?
So
still.
It depends how you do it. If you do it smartly so that it learns to deal with low precision while it's training, then you can get away with very little precision in the actual computation. You still need enough precision for storing the weights because they are accumulating a lot of small changes. So these guys need at least 16 bits, and they need floating point. So yeah, but I guess a lot of this is recent research papers over the last year, and more work needs to be done to try these different variants on different architectures and data sets. But the early results that basically what did that you can get away, in fact, with single bit computation on some architectures and data sets. But you still need a high precision on the weights when trained. Once you've trained, then you can quantize very, very aggressively and still get pretty good results.
So for us, the way we see it is as much as we can provide people with operations that are faster at every stage, we're going to do it. Sometimes it's easy to put it in the hardware. Sometimes it's slightly harder. And as I said, we're still generic purpose hardware, right? So each time you see a GPU, if you're interested in deep learning, I can only advise you to look at the FP32, FP16, and Int8 numbers. I don't know of, I know very few people in machine learning that look at 64. But in terms of like numerical computing, we see a whole range of people. So right now, as a beginner, FP32 is safe. That's what most of the framework implement by default. But research is very active, and we just want to make sure we support that correctly.
So you could go down as low as a single bit per weight, and it still work in terms of amount of computation. But the storage for you still need the storage when you train for those work.
Yeah, and actually, so that's a very good point too, because like when I showed the TX one before, the little teeny tiny platform, this was the first platform where we had FP16 built in the hardware, and the first code we published were actually we were very careful about the storage. We could do sometime FP16 for storage and not for compute. So what you're going to see and what you might want to pay attention to is the difference between the precision in the compute and the storage all the way around. So when we say FP16, you're going to hear a conversation like full FP16 or with that kind of consideration. Yes?
On the Inference engine, is there any complication or can you talk about the internals of it, like how does it work?
There is a great blog post written by Ryan.
It's on the Parallel for All blog post. I can give you a link.
And we'll be around until Friday if you want to talk to us about that. So before I go to CUDA, as I mentioned, to program correctly on the software side, you have to have an idea of what the hardware looks like. So I'm not going to go into a full GPU architecture class, but I just want to define a few terms. The GPU has two main components, memory and streaming multiprocessor, SMs. Okay? So the memory is where you store data by definition, and the SMs are where you do the computation. So the global memory of the GPU, you can see that as the RAM that you would have on a CPU machine. And it's accessible by both the GPU and the CPU. That's what we call the global memory. Right now, in GPUs, we see up to 24 gigs of global memory. So it's already much more than we saw some years ago. And you can have error checking on the memory in some GPUs in case you need it. So that's the part for storing data. For computing, GPUs use what we call SMs, so streaming multiprocessors, that perform the actual computation. So as Ryan mentioned before, each SM has its own control unit, register, execution pipeline, and cache. So the SM is actually the unit that performs the computation. OK? If it's not super clear, I'm going to have more drawings, so it hopefully it's going to get clearer. In each SM, you have many CUDA cores that are architecture dependent. They can do special function, like cosinus, sinus, whatever. Each SM has shared memory plus L1 cache. And they have thousands of registers. So that's what the drawing looks like, right? The cores, and that's what an SM is. So I already mentioned several types of memory. I just want to give like a little synopsis here. So I have the global memory, those 12 or 24 gigs I talked about. There is the L2 cache on top of it, underneath it, depending on you sit, it's going to sit on top of it. And then for each SM, you're going to have registers, L1 cache, and shared mem. OK? So the reason why I'm saying that is because when you're going to program, you have to be aware on where is what. It's going to be less and less important soon with unified memory, especially for the difference between global memory and local memory, but we're going to see that later. CUDA programming level. So I took care of the memory. Now I'm going to tell you how we compute on the GPU. So there is a part of the code which is serial code that executes on the CPU, whatever that CPU is. The parallel code executes on what we call the device. The device is the GPU. It executes through many threads across multiple processing elements. So that's basically what a CUDA C++ applications looks like. You have some serial code executing on the CPU, gets parallel on the GPU, back to the CPU, back to the GPU, and so on and so forth. That's why we care so much about communications, because if that process is not efficient, we can see it's going to be problematic. A quick example. So it's an example which is slightly more complicated than the one I've shown at the beginning. So here, what I'm doing is a simple vector operation where I do y equal a x plus y, which is what we call the SacSpy operation. So it's just basically adding to vector and adding a weighted vector, right? And so the first part is the standard C code. And the second part is the parallel C code. And as you see, it's parallel code, but there is no loop. The loop is encapsulated in that cryptic instruction which defines blocks, block dim, and thread. I have a mention of global memory at the top, and at the bottom, I launch a function which is called parallel, where I have the number of blocks, and I have that number 256 here that I'm going to detail afterwards. Okay? So basically what we do is we don't do the loop, but we provide a pseudo loop that is executing in blocks and threads and so on and so forth. Okay? So you've seen in the previous slide, I mentioned this is a SacSpy kernel. On the GPU, the parallel portion of the application, what's going to run on the GPU, we call that a kernel. An entire GPU can only execute a lot of kernels and many threads at the same time. The CUDA threads are defined to be very light, switching very, very fast, so that we can switch between threads very, very quickly. And we have thousands that can execute simultaneously. It makes it a bit difficult the first time you program it, because you have to think of all the things that are happening at the same time. But if you've been programming with languages like MATLAB or R, where you work on table, it's a bit similar. Okay? So again, vocabulary, the CPU is what we're going to call the host. I'm sorry, I can't pronounce the H correctly. It executes function. And the GPU, we're going to call it the device, and it's going to execute kernels. So when we say we execute either a kernel, it's on the GPU, and a function is going to be on the CPU. Okay for everybody? So CUDA kernel. A kernel is a function which is executed on the GPU. That's what I said before. And it's actually an array of threads. So that's what's defined on the right. All the threads will execute exactly the same code. They are all the same, but they can take different paths. And each thread has an ID, so that you can actually pinpoint it. You can select input-output data, and you can make control decision. Okay, so that's an example on the right, where I have a thread, I execute a function, and I have an output. So that's a thread.
So how many threads can there be?
So we're going to see that in the hands-on lab. It's going to depend on the GPU you have.
Let's say given some number of cores.
Yes. So each thread can have, so each core, I'm going to get to that. So here, each arrow is a thread. And thread can be divided into blocks. So a block is going to be a bunch of threads. Blocks will be grouped into a grid. A kernel is executed as a grid of blocks of threads. So when you execute a kernel, you actually push a full grid of block of threads on the GPU at the same time. So each thread, so that's the parallel between the software and the hardware here. Each thread will be executed by a core. With each thread block will be executed by an SM, and each kernel is going to be executed by the GPU, a GPU being able to have several kernels at the same time. Okay for everybody? So now I'm going to enter a subject which is a very difficult subject. It's cooperation. Since a lot of things are happening at the same time, sometimes you can cooperate, sometimes you cannot. So thread blocks, they allow cooperation. Inside the same block, the threads can cooperate. What this means, they can load and store memory they will use. They can share results with each other inside the block. And they can synchronize with each other. This is all inside a specific block, not outside a block. Thread blocks allow for scalability. What I mean by that is blocks can execute in any order, concurrently or sequentially. So you can see right away that having cooperation between blocks is not something you might want to have, because the blocks are supposed to be independent. And that's what gives you stability, scalability, and performance. So inside a block, you can do whatever you want. Outside a block, you have to be careful, because you don't control how and when it gets executed, right? And so a kernel scales across any number of SMs, and that's where it gets tricky. We're going to see that more in the hands-on lab, but you cannot cooperate between blocks, and especially you want to make sure you don't want to have blocks to wait for each other. That's not possible. Again, to memory. So I mentioned the hardware before. I'm just going to mention what it gives for the software part. So threads have register, their own little memory. they have local memory. And the block of thread has shared memory. So shared memory is defined like this. It's allocated per block, and it has the same lifetime of a block. When your block is gone, the shared memory is gone. It's accessible by any thread in the block. That allows for cooperation. And you can share data among threads, or you can manage on your own your cache, for example. This is particularly interesting when you do matrix operation and deep learning, when you do gems, because you can reduce memory access doing that. So again, register, local memory, each block of thread has shared memory, and all the blocks can access the global memory. The reason why I'm making a big fuss of it is like if you haven't played with it, you can say, okay, I'm going to put everything in global memory, and I'm going to be good. The problem is global memory is not as fast as local memory. So you want to make sure you benefit as much as you can from the different memory access so that you have the fastest access pattern possible. So the global memory is accessible by all the threads of any kernel, because the kernel runs on the GPU. Its lifetime is much longer. The data allocation is when you allocate, you got it, and when you deallocate by the host, the CPU. So for those of you that are used to that, usually if you use a framework, for example, you launch a workload, and you look at the GPU memory, you're going to see it being filled, and at the end, you're going to see the memory goes back to very few usage. And that's exactly what's going on. Okay? This is by opposite to the local memory that disappears when the thread's gone. Memory management. And I'm almost done. So again, CPU and GPU have separate memory spaces, and the data is moved across the PCIe bus for most of the GPUs we know. Now we can move some of it through NVLink, but I'm not going to enter that right now. So we can use function to allocate, deallocate, and copy, just like in C. We're going to see that in the hands-on lab. Pointers are pointers, like they are in C. They're just addresses. So if you have a pointer, you can't know where it is. You can't know whether that pointer is on the CPU or on the GPU. But as a programmer, you might want to know, because that might make a big difference. So you must check the attributes of your pointers to know where your pointer resides. So I'm sorry, it sounds like a lot of do and don't do that. But I just want you to have a summary of this, because you're gonna see that in the lab. We want to be careful when we're differencing, because if you dereference a pointer that somewhere where it doesn't exist, you will have a bad crash. And this is very difficult to find in the code. Even with a provider and everything, that's hard to see those, even with a debugger. So anytime you use a pointer, try to put a quick comment to know where that pointer resides. Allocation of memory and release. So it's basically like in C, except you add CUDA at the beginning. So CUDA malloc, CUDA metadata, CUDA free. This is an example. So again, we have that hardware-software balance. That what we call device memory is the GPU memory, and what we call host memory is the CPU memory. So CUDA mem copy. So that's an operation that sometimes is difficult to understand. So it only returns when the copy is complete, and it blocks a CPU thread until it's been copied. So what data transfer is, you start a CPU thread, it goes to the GPU, copy, and then blocks until it comes back. So if you want to be efficient, that's something you want to talk about. And it doesn't start copying until all the previous CUDA calls are complete. So you can't copy while something else is going on. I'm not going to go too much into the memcopy host to device and device to host and device to device. We'll see that briefly in the labs if you wish. And at some point, if you want to discuss, we can discuss unified virtual memory, but that's not something I'm going to cover here. But it used to be, and it's still the case, that copying from host to device had to be done by the developer. With what we call unified virtual memory, that's not going to be the case anymore. It's going to be automatic. And that's what's going on here. OK, just a basic execution and a summary of all I said. Parallel code on the GPU called a kernel is launched and executed on the device, the GPU, by many threads. Threads are grouped into thread blocks. Parallel code is written for a thread. So the loop, it's a thread. Each thread is free to execute whatever it wants. And we have IDs for built-in threads and blocks. Threads are partitioned into thread blocks. And the grid is all the blocks for a given launch. I'm sorry I'm reading, but it's just like I just want the vocabulary to be OK. A thread block are a bunch of threads that are synchronized and that can communicate via shared memory. IDs and dimension, which answer the question, how many threads? And I voluntarily won't answer that question. I'm doing that on purpose. I'm sorry. So why I won't answer that question is because the first exercise in the hands-on lab is actually for you to size your GPU by playing with block ID and number of threads. So threads are 3D. They are unique within a block. Blocks are 2D, two-dimensional. And they are unique within a grid. And dimensions can be set at launch time. So in the hands-on lab, we start with a one-dimensional for it to be simpler. But then you can use two-dimensional or three-dimensional. And the built-in variable we're going to use are thread index, block index that give the IDs, block dimension, grid dimension. And each GPU will have different SM and will have different values that are optimal for it. So sometimes you hear, oh yeah, I got GPU code, but I don't have it tuned. Most of the tuning from one generation of GPU to another occurs at that level, making sure the kernel we launch are the exact site. And if you look, it's very funny because I was very surprised the first time I looked at the AlexNet paper. If you look at it from an engineering perspective, Alex Krzyzewski did a wonderful drawing, because when you see the drawing, you basically see the GPU he was working on. And that's very nice, because it showed that that paper was actually made to be running on the GPU, or the sizing were actually adapted to the GPU he was working on. And that's where the link between the actual dimensions sometimes of the network and the hardware is so stringent. That's an emblematic example. Nowadays, it's not as stringent. But having an application well-sized for where it lives usually makes the performance very, very impressive. And actually, that first code, like CUDA Component 2, was extremely stressful on NVIDIA GPUs for that reason, because it was using all the tuning a GPU could have at a time. OK, another drawing, thread, 3D IDs, union with a block. We got it, you got the picture. How do you do that on the GPU? There is a special syntax, which is the triple chevron notation. And so I'm not going to spend a lot of time on it, but that's what it looks like. Kernel, lower than, 32, 50, 12, like greater than the chevrons. And that's how you define your sizing. So it's just a quick additional, another word. A kernel launches on a grid of blocks. Each block is launched on one SM. And we also have another term, which is called a warp, where a block is divided into warps of 32 threads each. It's a 32-way vector. So you might want to have it a multiple of 32. Because all the warps execute the same instruction simultaneously, and that's very linked to the hardware. The blocks runs to completion on an SM it's starting on. So you can't interrupt a block to do something else. So when you design, keep in mind that the block has to complete. If a block doesn't complete, it doesn't work. There is no migration. You can't move it at all. The blocks must be independent. We already tackled that a bit before. Be careful, they cannot synchronize, no lock. So if you're used to parallel programming, sometimes on a different architecture, that's where it gets tricky. There is no synchronization, and this is essential to scalability. Okay, I'm done. Questions? So I won't answer that question. Sorry. Yes?
Yeah, these IDs about 3D and 2D. Is there a meaning to those dimensions?
Please say that again.
There are like dimensions to these ID addresses. Is there a meaning to these dimensions?
Is there a what?
A meaning.
Oh, meaning, sorry. Yes, because if you have 32, so we're going to see that, that's it. I mean, I see that as the same question. So is there a meaning to the block size and size ID? It's depending on how many threads and blocks your GPU can execute. And so you just want to size it so that it's a good combination between what your application has to do and what your GPU looks like. So on purpose, the first question of the hands-on lab is for you to understand that meaning by sizing it. Right? So it's directly linked to hardware. It's just pushing blocks that fits the size of your GPU. Does it answer the question? Any other question? Okay, so your time to work. Okay, everybody, I only have 5 minutes left, so I'm going to be around during the break and keep on answering questions in you wish, but I want to wrap up with everybody. A quick thing. In this lab, we're running on Amazon, on an Amazon instance. But the software that is running on Amazon is the same everywhere. It's available on nvidia.com, get CUDA. It's free, and it works anywhere. The reason I'm saying that is because I see a lot of people with like funny laptops, as I said at the beginning, and that's why I have a gaming laptop. I don't play games. I'm very bad at it. I get destroyed by people each time I start. But people look at my laptop like, wow, no. So the only thing I do with my laptop is what you've seen today. And so this is running locally on my laptop. And it shows you what we ask you to do at the end of the lab. And it shows you the characteristics of the GPU that is in my laptop. And finally, I'm going to answer your first question. Here, you can see those numbers of the sizing of my GPU when I do what is called a device query. It's a sample which is provided with the CUDA software, and it gives me the characteristic of my GPU. So the GPU I have here is a GTX 970M. It's a Maxwell GM204 GPU for laptops. The maximum number of threads per block that I can have is 1024. And the maximum number of threads per multiprocessor is 2048. And my warp size, as we discussed before, is 32. So that's how you know what you can do. And at the end of the lab, they ask you to do the same on the processor you're using. You're going to see it's slightly older generation, but that's what it is. So if you're interested in trying, if you have a laptop, it works on your laptop, whether you have a Mac, a Linux, or a Windows laptop, if you have an NVIDIA GPU. Yes?
So how many multiprocessors are there?
So here, I have 1,280 CUDA cores. So that's how I can do it.
So there are less cores than the number of threads that you can run?
That's right. Yes. So the number of threads I have per multiprocessor, yes. Okay, so that's what I said. That's the amount of memory. When I'm running something, that's where I can see whether it's running. So I invite you to have a look at this. I invite you to do that in the lab. You can do that at the end of the lab. You'll have the commands and everything to execute that. If you want to keep on trying, so as I said, the lab is going to be open for a few days. And then we have a full lab platform on nvidia.quicklab.com. So if you register for that lab during that time, you'll get free credits to be able to do a lot of labs on that platform. And if you have any question, I'm not always very responsive, but you're always welcome to send me an email and bug me until I reply. I usually do. The last thing is I'm going to do like everybody. I didn't have a lot of time to show that. We're hiring, like most of the companies. We're having a lot of fun. We have a full research program. We have an applied research program. We have a full automotive section. We have a lot of different types of jobs, including sales jobs or technical jobs. And you're welcome to talk to Ryan, to me, or Penn is here too. So if you're interested in joining NVIDIA, we're very happy to talk to you. And thank you very much. I'll answer all the questions during the break.